This is the Chapter 11 practice for Chemistry 1032C, and Chapter 11 is an introduction to organic molecules and functional groups. Question 1 wants us to look at formulas of compounds and identify them as organic or inorganic. Organic compounds, you need to keep in mind, are going to have carbon as their main element. I kind of think of it as carbon-based. If there is no carbon, then we won't classify it as an organic compound. Other elements could be included in an organic compound, such as nitrogen, oxygen, hydrogen. But the bottom line is it's going to be carbon-based. So letter A, water. Water does not have carbon, so we classify it as inorganic. The element bromine also is absent of carbon, and so we are going to classify it as inorganic. Now letter C, C6H14, which would be hexane, you notice there's the carbons and hydrogen, so those carbons there tell us that this is an organic compound. Sodium chloride is a salt, and those are inorganic. It's an ionic compound. And then the last compound is carbon-based with the CH3, CH2, and so it is organic. So for this introduction to organic chemistry, we're going to use the simple definition that organic compounds are carbon-based, and that's how we will distinguish between organic and inorganic compounds. Now number 2 wants us to complete each structure by filling in all hydrogen bonds and lone pairs. I'll move from left to right, and then if there's something above or below, I'll do those next. So what we need to keep in mind is that carbon likes to have 4 bonds. So when we look at the first carbon in letter A, it has a triple bond, which is 3. So I'll add 1 hydrogen there to finish it off and have 4 bonds. Now the carbon to the right of that has 4 bonds already, so no hydrogens would be added. Now the next carbon has 1, 2, 3 bonds, and so I would need a hydrogen to make it 4. Finally, the last column, the carbon, the furthest to the right, only has a single 1 bond, and so then we will add 3 hydrogens to it to finish it off. Now I actually want to move that hydrogen over just a little because looking at the chlorine, I am going to need to add some lone pairs to the chlorine. Chlorine is a halogen and it has 7 valence electrons. So chlorine only needs 1 bond, but it wouldn't have an octet, so the halogens have 1 bond and then they have 3 lone pairs. I'll try one more time with these. Let me see if my marker is the thinnest as possible. Okay, let me try and see. Well, it doesn't really help too much. But there we have the 6 pairs. Okay, so let's look at the next one. Now starting from the left, I see a nitrogen. Nitrogen has 5 valence electrons, so that means it would like to have 3 bonds, because the number of valence electrons plus the number of bonds equals 8. So nitrogen would like 3 bonds. It has 1 here, so I'll add 2 more bonds. And then with the 3 bonds, it would also like 1 lone pair. Moving to the right, the next carbon has 3 bonds, so to make 4, which carbon likes, I'll add a hydrogen. Continuing to the right, the next carbon has a double bond to an oxygen, which would be 2, and then 3 and 4, so the next carbon is okay. Now the oxygen furthest to the right has one single bond, so we're going to write a hydrogen attached to it. That would give it 2 bonds and then 2 lone pairs. Now you might wonder why I didn't draw a double bond, and there's a variety of reasons. One might be it's because the instructions only said I could add hydrogens and lone pairs, that I couldn't change the bonds. So that's one thing. The second thing is, if you start looking at it, if I made that single bond, the last single bond, a double bond, my carbon would have more than 4. Now the double bonded oxygen needs to have 2 more lone pairs on it to complete the octet. And finally, the carbon here on the bottom would need 3 hydrogens to finish out the 4 bonds. And those 2 hydrogens look kind of close together. Maybe I can write the hydrogen. Let me write them closer, see if we can make it look a little neater, even though I have well, kind of. Now let's look at the last one. Again, I'll start with the carbon parts and I'll go from left to right. The first carbon has 2 bonds, so I would add 2 hydrogens to make 4 bonds. The next carbon has 3 bonds, so I would add 1 hydrogen. The next carbon has 3 bonds, so I would add 1 hydrogen. This final oxygen has 2 bonds, and oxygen with 6 valence electrons likes 2 bonds, so I'll add 2 lone pairs. Then looking at the oxygens on the top of this structure, they each have 1 bond. Oxygen likes 2 bonds, so I'm going to add a hydrogen to each, 2 hydrogens total, to make the 2 bonds, and then 2 lone pairs. So we can use the octet rule and the number of bonds that each of these elements like to form to help complete structures. Another thing they would like us to do is to determine the shapes, and this one asks us to determine shapes around indicated atoms. I refer you to your book on page 348. There's table 11.1. You do not need to memorize this table. Table 11.1, page 348. This table tells the different shapes. Now what we're going to do, so like on number 1, it says, determine the shape around the indicated atoms in each compound. Don't forget to add lone pairs to heteroatoms. And a heteroatom is anything that's not a carbon or a carbon. Yeah. Before determining the shape around them. Okay, so I can add a nitrogen here needs a lone pair. Now the truth is that will not change my shape, because the only lone pairs that would change shape would be ones that are on the molecule I'm determining the shape of. So let's go back, and if I look at number 1, I'm looking at this carbon right here, and I see that this carbon has 1, 2, 3, 4 bonds and 0 lone pairs. And so number 1 is, with 4 bonds and 0 lone pairs, it's tetrahedral. Now number 2, I'm looking right here. Oh, wait, just a second. I need to make a correction because I erased this because I was getting ahead of myself. And looking at the shape here, it's not tetrahedral. It does have 4 bonds, but if I went on that, every single thing would be 4 bonds. So what we want to do is you want to look at how many atoms it's attached to. And so this is it. Oh, wait, that looks awful. I was trying to make it so I could draw what atoms it's attached to. Let me see if I can change the pen a little. Okay, so it's 1, 2, 3 atoms that it's attached to. So number 1 has 3 atoms and 0 lone pairs, and so this is trigonal planar. And I'm not spelling it all the way out because of the space. Now number 2, I'm looking at this carbon right here. And so I would say, okay, that carbon has 2 atoms around it. So it just has 2 atoms. 0 lone pairs, and so this would be, this one, number 2, would be linear. Okay, so this is number 1 is trigonoplanar, and number 2 is linear. Okay, so let's take a look at the other ones, the next one. So looking right here, so I'm looking at number 1, and I look and it's attached to 2 atoms. Now, what did I do wrong? There's 2 atoms, but I did not follow my own recommendation, and that's put in lone pairs. But oxygen is not happy with just 2 bonds there, is it? Oxygen needs 2 lone pairs on it. All the oxygens would need 2 lone pairs, but it's going to change the shape. So this has 2 atoms and 2 lone pairs. And if you look that on your table, up on your table, that is bent. Now, number 2, this is a carbon right here. Now, carbon would have 1, 2, 3 bonds, which isn't enough. But remember, in the skeletal structure, they take out the H's that are attached to the carbons. So there's actually another H there. So when we're looking, it's attached to 1, 2, 3 atoms. And number 2 is trigonal planar because it has 3 atoms and 0 lone pairs. Okay, so number 3. Now I want to, if you don't mind, I'm going to take this little section and write it out. So I have, it's attached to my ring, and then I have CH2, then I have a C and an H, and then a CH3, then I have an N, an H, and a CH3. And on my N, I would have to have a lone pair. So it has me looking at, number 3 would be looking right at this guy right here. And so when I look at this guy, it has 1, 2, 3, 4. It's attached to 4 atoms and 0 lone pairs. So number 3 is tetrahedral. Now the other one is this nitrogen right here. And so looking at the nitrogen, it's attached to 1, 2, 3 atoms, and then there's 1 lone pair. And so this is trigonal pyramidal. And I can't fit it, but it's trigonal pyramidal. So number 3 is tetrahedral. Number 4 is trigonal pyramidal. Number 1 is bent, and there's a lot of them here. And number 2 is trigonal planar. Now another thing they ask us to do is convert compounds into condensed structures. And so that's where we bring all the hydrogens next to the carbon together. So this would be I'm starting with this carbon here, CH3, and then CH2, I have it 1, 2, 3, 4, 5 times. So then you can put a parentheses and put a 5, because there's 5 CH2s. And then I would have an O and an H. Now this next one, I'm going to start here. This is a CH3, and I'm going to show you there'll be 2 ways. And then this CH3 is attached to this CH, And then there's another CH3 sticking out here. Then we have C double bond O, O, that gets that. Then we have this one, which is CH2, and this one, which is CH3. Now we actually could condense this even more, because do you see that there's a CH3 and a CH3 right here? So you could write CH3 with a 2, then your CH, then because there's 2 oxygens on the carbon, you could write CO2, and then CH3, whoops, sorry, would be CH2, CH3. Now I would accept this first way that I wrote, but the other way is also completely acceptable. Now another thing we're able to do and try to work on is identify functional groups. And to identify functional groups, I'm not asking you to memorize the different functional groups. So what you would need to do is get the tables in your book that help you identify the functional groups. There's lots of them, and they are on your book on page 355 and 357. So there's 3 categories. There's one that just have carbons and hydrogens, called hydrocarbons. There is one where you have heteroatoms that are attached with single bonds. And then there's a whole table of functional groups that have a C double bond O, which is called a carbonyl group. Now, when I'm looking for functional groups, what I look for is things, heteroatoms are the first thing I look for. So on this first one, I noticed there's oxygens here, there's oxygens and hydrogens here, and then there's here and here. So I actually have 4 different things to identify. Let's start with the ones on the top, the 2 OHs. Now these are carbon attached with a single bond to a heteroatom. And if you look on the second table, an OH group is called an alcohol. Now we study functional groups because they are sites for reactions, they help us predict properties, they help us classify compounds, and they help us name them. And so as you work more with chemical compounds, a lot of times it's important, for example, to know that they have an alcohol group. Now these side functional groups here, these two are also the same functional group. If you look at them, they're mirror images. So on these, I see the carbonyl group, which is the C double bond O right here. Now this, anytime you're attached to carbons and hydrogens on the table, that's going to be an R. So this has a C double bond O right here. It's attached to an R, and then on the other side, it's attached to an OH. So looking at the table, you'll see that if you have a carbonyl, a C double bond O, and one side has an R and one side has an OH, that this is called a carboxylic acid. Now both of these are the same, they're just mirror images of each other. Now let's look at letter B. Well, I see right here in nitrogen, that's going to tell me that it has a functional group. I see an OH on oxygen, there's a functional group. And then this big ring here is also considered a functional group. It's on the hydrocarbon table. Well, I recognize OH from the previous one as an alcohol. This one here with the nitrogen, there's only 2 nitrogens. There's an amine and there is an amide. If you find these on the table, the difference is the similarity is they both have nitrogen. The difference is the amide has a C double bond O group, or a carboxylic group. Well, mine doesn't have that on this example, so it's not an amide. This is an amine. Now this big group that has a double bonded every other one, the 6-member ring with double bonds every other one, and it's a carbon ring, this is called an aromatic hydrocarbon, or they may also call it, this one in particular is benzene. Now letter C is the last one, and I see right here this carbonyl group. Now what's very important with carbonyl groups is you look what's on either side of them. And in this particular example there is a nitrogen. Remember, I told you in nitrogen there's only 2 different nitrogen ones that we'll encounter, amine and amides. And the difference is the amide, the nitrogen is next to a carbonyl, or a C double bond O. And that's what I have right here. So this is not an amine, but this is an amide. Now another thing one other thing we can do is, if we know the functional group, we can actually draw compounds. Now you might be able to draw more than one correct compound to fit the description. So I'll only draw one of them. If you think you have a right one and want me to check it, send me a picture of it and I'll let you know. So when I'm drawing these, I start with the functional group. So this is an alcohol. So I look up, and an alcohol is OH. And the OH is attached to an R, or carbons. Now this example I need 3 carbons, so I would add 1, 2, 3. Now you might think, great, it's finished. But remember, how many bonds does carbon like? 4. So I'm going to take, and to finish out each of my carbons to have 4 bonds, I'm going to add hydrogens. So that makes 4 here. That makes 4 there. And this makes 4 here. So this is propanol, and this is a 3 carbon alcohol. Now, what's another thing? An alkene. If you look up an alkene, this is a double bond. Sorry, alkane is a single bond, alkene is a double bond, and alkyne is a triple bond. So alkene is a double bond. Now we have to have 5 carbons. 1, 2, 3, 4, 5, and somewhere I need a double bond. So I'm just going to put the double bond right there. Now there's other places you could put the double bond. In fact, you could put more than one double bond and you would still have an alkene. So I'm just going to leave mine like this, but I have to finish it off because remember, every carbon has to have 4 bonds. So if it has less than 4 bonds, you can add hydrogens to complete the structure. Now again, you may have put your double bond in a different place, or you may have added more than one double bond. You would still have an alkene with 5 carbons. Now the last one is we're writing a ketone with a molecular formula of C4H8. So we have to look up ketones, and ketones have a C double bond O. If you look it up on the table, they have a C double bond O with R's on either side, and the R's are just carbon groups. So I'm going to start with the C double bond O, and now I have to add carbons on either side. So I know I have to have at least 1, and that would be 1, 2, 3 carbons. But here I need 4 carbons, so I'll add 1 more. It doesn't matter which side I add it to. So right now in my structure I have my 4 carbons and my 1 oxygen, and I need to finish off by adding hydrogens, and I will add hydrogens So everybody has 8 electrons or 4 bonds. And I'm going to count up my hydrogens at the end and make sure that I only used 8. So 1, 2, 3, 4, 5, 6, 7, 8. So there's a ketone that has the formula C4H8O. Now finally, this last question has to do with the properties of organic compounds. Skin moisturizers come in 2 types. One type is good, composed of mainly hydrocarbons. The hydrocarbons are going to be nonpolar substances. Suggest a reason as to how moisturizer of this sort keeps skin from drying out. So, if it's nonpolar, then it does not like to come off with water. So it does not like water because water is polar. And we know that like dissolves like. So if you put this type of moisturizer on, it will hold the moisture in because when water is placed on it, it won't just rinse off and wash off with the water. So it will stay on your skin, moisturizing it and not rinsing off with water.